Dear students, in this teaching unit we are dealing with the electrical connection of solar cells in a solar module. Now we have learned a lot about solar cells. You know how a solar cell works, how it is manufactured, and what a standard solar cell looks like today. In this unit we'll now look at how solar cells are made into solar modules. A PV module consists of several solar cells that are connected together. We can connect solar cells together in different ways. One way is a series connection. Here you can see a series connection of 3 solar cells. The connected solar cells are also called a string. In a series connection, the voltage adds up while the current is the same everywhere. For simplicity, let us assume that all the currents and voltages in the individual cells are identical. This means that in the circuit shown here, the voltage is 3 times as large as that of a single solar cell. The current in the circuit, on the other hand, is the same as that of a single cell. Another way to connect the solar cells is the parallel connection. In the parallel circuit, the voltage in all cells is the same, but the currents add up. Let's take a look at how the interconnection of solar cells affects the UI characteristic. The characteristic curve of a single solar cell is shown here. If we now connect 3 of these cells in series, the voltage adds up while the current remains the same. The resulting open circuit voltage is therefore 3 times that of a single cell. On the other hand, if we connect the cells in parallel, the short circuit current triples, while the open circuit voltage is the same as that of a single cell. Now, ohmic losses occur in the solar cells and in the cell connectors. The power losses, however, result from the product of the resistance and the current squared. The power losses therefore increase with the current to the square. Thus, the current should be kept as low as possible. For this reason, the series connection is usually preferred. Here you see again a series connection of 3 solar cells. For simplicity, we have now assumed that all 3 solar cells are identical and supply exactly the same current and voltage. Unfortunately, this is not always the case in practice. For example, let's assume that one of the cells in the string is shaded by a leaf, for example. We have learned that the short circuit current is proportional to the irradiance. If the cell is completely shaded, it no longer produces any current at all. However, the other 2 solar cells continue to produce current. As a result, a negative voltage is now present at the shaded solar cell. Due to this voltage, it changes to blocking mode and is now operated as a consumer by the remaining 2 solar cells. As a consequence, the shaded solar cell heats up. A hotspot is created in the circuit. If, as in a solar module, a large number of solar cells are connected in series, or even several solar modules, in the worst case the hotspot effect can lead to the destruction of the module or even can cause a fire. Let's see how shading affects the characteristic of a string. The short circuit current is proportional to the irradiance as mentioned above. Let's assume that the irradiance decreases by 75% due to shading. So the short circuit current of the shaded cell drops to 25%. The open circuit voltage of the shaded cell also drops slightly. The other 2 cells continue to produce the full short circuit current. which now flows into the shaded cell. However, the shaded cell cannot pass it on completely and blocks current flow when the current is higher than its own short circuit current. In this case, it switches to reverse bias mode and is now operated by the remaining solar cells as a consumer in the second quadrant. But what is the operating point of the shaded solar cell? Since the shaded cell is operated in reverse direction, we mirror the IV curve of the two unshaded cells at the current axis. The intersection between the two IV curves gives the operating point at which the shaded cell is operated. Almost the entire voltage of the cell string drops across the shaded cell. We can obtain the characteristic curve of the cell string by adding the voltage of the individual cells for a given current. Compared to the characteristic curve of the unshaded string, we see that the current is now almost completely determined by the shaded cell. Although only one cell was shaded, the maximum power of the entire string is reduced by almost 75%. To prevent this dramatic drop in power and the associated hotspot effect, so-called bypass diodes are used. These bypass diodes are diodes that are connected anti-parallel to the strings. As we learned in the first week, a diode blocks current flow under negative voltage and conducts it under positive voltage. As long as no cell is shaded, no current flows through the bypass diodes, so they do not interfere. If now the cell is shaded, a negative voltage is applied to the cell. The bypass diode above the cell now conducts the current and the shaded cell is bypassed. Here you can see again the IV curve of a shaded and an unshaded cell. The bypass diode now bypasses the shaded solar cell when the current of the other two cells exceeds that of the shaded cell. So in this voltage range, the cell string operates as if the third cell did not exist. If we now approach the open circuit voltage, the current decreases until it finally equals the current of the shaded cell. The shaded cell now no longer needs to be bypassed. So the IV curve in this range is as if there were no bypass diodes. You can see that the overall IV curve of the shaded cell string has significantly approached that of the unshaded string. It is quite similar with the power characteristic curve of the string. Without bypass diode, the maximum power drops to about 25%. The degree of the power drop corresponds approximately to the degree of shading of the solar cell. So if the solar cell would be shaded only 10%, for example by a bird droppings, the power of the cell string would be reduced by 10%. But what happens when bypass diodes are added to the circuit? The power characteristic now has two local maxima. The lower maximum corresponds to that of a shadowed string without bypass diodes. The higher global maximum corresponds to that of two unshaded cells. The MPP in this case is about 2/3 of the unshaded string. Here you can see a solar module as it was standard until a few years ago. In such a module, 60 or 72 cells are usually connected in series. The series connection offers the advantage of low current and comparatively low ohmic losses. However, as we have just seen, This raises the problem of shading. Therefore, bypass diodes are integrated into the circuit. Ideally, each solar cell would have its own bypass diode. In practice, however, this is not done. The bypass diodes are installed in the module junction box on the rear side of the module so that they can be replaced in the event of a defect. For practical and economic reasons, the number of bypass diodes is therefore limited, and the solar cells are divided into several strings, each of which receives a bypass diode. If a solar cell in one of the strings is now shaded, the corresponding bypass diode bypasses the string. By bypassing the shaded string, the module power drops by 1/3. Only 67% of the module is active. If now an even larger part of the module, including cells from string 2, are shaded, string 2 is also bypassed. The module output drops to 33%. The situation gets even worse if the module is not shaded from the side but from the bottom. This case occurs, for example, in ground-mounted systems where the module rows are too close together. Now cells from all 3 cell strings are shaded. As a result, all 3 cell strings are bypassed by the bypass diode. The power of the module decreases to 0 watt as a result. For some years now, the solar cells are cut in half before interconnection. This is mainly due to the increasing size of the solar cell. This halves the current supplied by the cells. Since the current is squared included in the power losses, these losses drop to 1/4 compared to the full cell module. So instead of a 72 full cell module, we now consider a 144 half cell module. Let's look at the interconnection of the cells. First, the cells are divided into 2 strings connected in parallel. One string in the upper half of the module and one on the bottom half. Within the 2 strings, the cells are connected in series in 3 strings. This type of connection ensures that the current and voltage of the module are the same as those of a full cell module. This is especially important with regard to the remaining system components. In addition to the lower ohmic losses, there is now another advantage in the case of partial shading of the module. In the half cell module, the bypass diodes are located between the 2 parallel connection strings of the module. Thus, 2 strings share one bypass diode. This has an effect on the formation of hotspots, among other things. Since the current in a bypassed string is only half as high, the power dissipation in the shaded cells is also reduced. As a result, they heat up less and module degradation over the module lifetime decreases. Let's take a look at what other advantages the half cell technology brings. In the case of shading, as shown here, only one of the 6 parallel strings is now shaded instead of one of 3, as in the full-size module. For the sake of simplicity, we assume complete shading. In other words, the strings really produces no electricity at all. The upper part of string 1 continues to produce current. However, since the bottom part no longer produces current and both are connected in parallel, the current of string 1 is only half compared to the other 2 strings. From the point of view of the other 2 strings, their current is thus throttled to 50%. In order to find out which module power can be achieved, we look at the IV curves of the module. As said before, the current of the string 1 is only 50% compared to the other 2 strings. Therefore, this string is completely bypassed at higher current levels. So, although only one of 6 substrings is shaded, only 4 substrings contribute to current production here. However, if the module is operated at higher voltages, the current drops below 50% of the normal short circuit current. Now string 1B again contributes to the current production. So while the current would now drop to 0 for the full cell module, the characteristic curve of the half cell module runs a bit further. If we also look at the power characteristic curve, we see that there are now 2 local maxima. One maximum for operating with bypassing of string 1 and one for operating without bypassing. You can see that it is more favorable to bypass string 1 completely. The maximum module power therefore drops to 67%. So for this type of shading, there is no advantage for the half cell module compared to the full cell module. It becomes interesting when more than one string is shaded. Let's assume that a larger part of the module, including cells from string 1B and 2B, is shaded. At high currents, the result is now the same as in the last case. Strings 1 and 2 will only produce half the current, while string 3 will continue to produce the full current. Therefore, both strings are completely bypassed at higher currents. In this case, the module power is only 33%, because only 1/3 of the cells contribute to the power production. This would also be the maximum possible power that a full cell module could deliver with this kind of shading. However, if the module is operated at a current below half the short circuit current, the situation changes. Now both strings 1A and 2A can contribute to the power production again. So all 3 strings are working at half the current. Thus the module power is at 50%. The situation is even more extreme if we consider the third case of a complete shading of the bottom strings. In this case, the full cell module no longer produces any current at all, since all strings are bypassed. With the half cell module it looks more favorable. Here all upper strings produce the same current, therefore none of them is bypassed. So 3 of 6 strings contribute to the current production. The module output is 50%. Let's compare the shading situations of the half cell and full cell modules again. If one of the 6 strings is shaded, both modules still deliver 67% of the power. If the shading increases to 2 of 6 strings, the power of the full cell module drops to 33%. For the half cell module it is still 50%. If the bottom half of the module is completely shaded, the power of the full cell module drops to 0, while the half cell module continues to supply 50%. Let's summarize. We have learned about the series and parallel connection of solar cells. While the parallel connection is associated with higher ohmic losses, in series connection the shading of individual cells turns out to be problematic. Today's standard solar module consists of 120 or 144 half cells in which bypass diodes are used to reduce shading losses. Lastly, we have seen that identical shading has different effects depending on the module design. Thank you for your attention.